So yesterday I told you that the standard model is based on a gauge symmetry which is invariant on the SU3 colors plus SU2 left plus U1 ether charge. And we spent quite some time actually yesterday to identify an additional global symmetry of the standard model, which is as equally important actually, which was the custodial symmetry. And I told you that there is the Lagrangian is invariant on the SU2 left cross SU2 right, which is the same thing actually at SO4. And this symmetry, this global symmetry, is broken by the vacuum into the SU2 diagonal. So that's the remaining unbroken symmetry of the vacuum after electric symmetry breaking. So now, probably you know this famous theorem by Boson associated to the breaking of global symmetry. So custodial symmetry is a global symmetry. You know this Boson theorem, which is telling you that every time you have a global symmetry which is spontaneously broken, then there is some massless Boson boson associated to it. So here you can count the number of Boson bosons. So SO4 is dimension 6. SU2 is dimension 2. Is dimension 3, so 3 plus 3 is equal to 6. It's broken down to SU2, which is dimension 3. So at the end, you expect exactly 3 Boson bosons. And what happened, of course, is that those 3 Boson bosons are actually eaten by the Higgs mechanism to actually become the longitudinal polarization of the W and the Z. So it's true that those Boson bosons in principle are there in the spectrum, but they don't appear as massless Boson bosons, they simply appear as some longitudinal polarization of the massive gauge field. That's why it was, in a sense, very important to identify these symmetries, because those symmetries are really dictating, what those longitudinal components of the massive gauge field are. So W plus minus and Z. And later, towards the end of the lecture today, we will see actually how to really describe the physics of those longitudinal polarization in terms of the physics of these Boson bosons. And clearly the longitudinal polarization of the massive spin 1 particle is very special because this is something which is associated to the mass. So you certainly know that in quantum mechanics, right, a particle of spin s has 2s plus 1 degrees of polarization. Right? That's the basic rule of quantum mechanics. But there is one exception to this rule. If the particle is massless, you know that, for instance, the photon is spin 1, so it should have 3 degrees of polarization, but you have all learned in optics that the photon has only 2 polarizations, the 2 transverse polarizations. And this is true only because the photon is a massless object. While here, the W and the Z, we know since the 80s that they have a mass of the order of 100 GeV. So they have a third physical polarization, which is the longitudinal polarization. And you can check explicitly that this polarization actually decouples when the mass of the spin 1 goes to 0. So, in a sense, the question was in the 80s where those longitudinal polarizations are coming from, right? You start with the theory in the unbroken phase, you have two degrees of freedom, the 2 transverse polarization, then you break the symmetry and suddenly there is a third physical polarization, which is the longitudinal one. So one of the questions at that time was really understanding where these polarizations are coming from. And one of the classical answers, maybe the answer that nature has chosen, is that actually those longitudinal polarizations are part of the famous Higgs doublet. In a sense, you start with the Higgs doublet, which is, as we have seen yesterday, 4 real scalar fields. Among those 4 real scalar fields, 3 of them are actually corresponding to the Boson boson. And there is one, this particular realization, there is one additional physical degrees of freedom, which is the famous Higgs boson. So here you already understand the difference between the Higgs doublet, right, and the Higgs boson. The Higgs doublet is mostly what has been discovered in the 80s, right? They are mostly the longitudinal polarization of spin 1 particle. And what has been discovered last summer is really this additional scalar field. Okay. So as I said, towards the end of the lecture today, I will give you some effective description to really understand the physics of those objects, because they are really important. They are, in a sense, the basic object of the electric symmetry breaking sector. They are 3/4 of the Higgs doublet. So you better need to understand first those ones, and then tomorrow we'll also extend this description of the physics to really describe this additional particle that has been discovered. But before doing that, I would like actually to come back to some of the questions that were asked during the lecture yesterday, which is, in a sense, how good is a standard model in describing experimental data. So if you want, how can I compare the theoretical prediction versus the experimental data? So in a sense, the standard model has a limited number of parameters, right? Basically, there is the gauge coupling. So if I forget, for the moment, I will forget totally QCD, right? QCD is a separated sector. It is important, of course, even if you want to do Higgs physics. I mean, you cannot neglect QCD because, as we have said yesterday, I mean, the Higgs is mostly produced by gluon fusion, right? So the gluons are playing an important role. But nonetheless, to describe all the electric observable, you can totally forget about QCD. So in this case, your theory will be described by 3 variables, which is gauge coupling of SU2, the gauge coupling of U1, and the Higgs expectation value V. And out of those 3 variables, you can now compute many observables, right? So for instance, you can compute the mass of the Z, you can compute alpha electromagnetism, you can compute the muon lifetime, which is associated to the Fermi constant. And then there is an additional one, like the mass of the W. So which one I've taken this? Well, let's say the decay width of the Z into a charged lepton, so E plus, E minus, something like that. So clearly, here, you see that you can compute many things in terms of only 3 input variables. So this means that in principle, you get some prediction. So now what you want to do is to test those predictions in some sense. So those input parameters are not physical observable, right? So what you do is that you identify those input parameters in terms of 3 observable. And usually, you take the 3 best known observable, which are those. Then there is a one-to-one correspondence between those 3 observable and those 3 input parameters. And then, basically, you can compute, then you can get some prediction for the other variables. And you want to compare those predictions with the experimental data. So, well, this correspondence is quite easy. I mean, at least if you're working at 3 level, right, forgetting about all the quantum effects. You know, for instance, that alpha electromagnetism, as we have seen this morning in the atomic physics lecture, is E squared divided by 4 pi, and E is nothing than this particular product of the gauge coupling, G times G prime divided by G squared plus G prime squared. Just looking basically at how the photon that we have identified yesterday coupled to the electrically quarks on the left. So we identify E. What about LZ? So LZ squared, we have seen yesterday that it's 1/4 G squared plus G prime squared times V squared. The last one is a little bit more complicated, G Fermi, where G Fermi is, in a sense, defined by the muon lifetime. And the muon lifetime, you can compute it here, and it's simply a muon decaying into the muon neutrino. then there is an emission of a W, and then this W gives you an electron and an anti-neutrino electron. So I assume that you know how to compute those Feynman diagrams. If you're not, I mean, maybe we can meet tonight in front of a glass of vodka, and then you'll be able to compute easily these diagrams. So then, from this diagram, you can compute the lifetime of the muon, which is something like the muon, the mass of the muon phi, G Fermi squared, times divided by 192 pi cubed. And then, if you're after drinking a lot of vodka, then you can even compute the correction. For instance, the correction due to the fact that the electron has a tiny mass, but is not zero mass, so you can compute this correction. It's something like -8, the mass of the electron divided by the mass of the muon. And if it's really late in the evening, then you can even compute a lot of QED correction. The fact that, you know, here you can attach a lot of loops of some photons, for instance, here. This gives you some QED correction. And people have spent their life in computing these things, so not only at one loop, but probably up to 3 loops in QED at least. And then it gives you some correction of the form alpha electromagnetism divided by the thing here, it's 2 pi. And of course, these things has been measured quite well. I mean, it's something like 2 × 10⁻⁶ second minus 1. So from this, and if you know also the mass of the muons, clearly you can determine a G Fermi quite well. Okay, so using those expressions, basically, you can really identify the 3 parameters here, and then compute the prediction for the other variables. So for instance, MW here, so MW, as we have seen yesterday, MW squared is 1/4 G squared D squared. So this means that you can really compute MW in terms of the other observables. And then you open the particle data book and check how much, you know, the theory is good, right, in predicting the numbers. So we will find all the details in the note. Maybe I will distribute some notes later on. And if you compare the theoretical prediction versus the experimental data, you will see that the theory is about 15 sigma away from what the theory is predicting. So it's quite bad, right? Everybody is telling you that the standard model is a beautiful theory that works very well. You do a simple computation like this one, and you find 15 sigma away. It's even worse if you look at some asymmetry, I mean some left-right asymmetry for the decays of the Z. So that's defined sin squared theta effective, which is simply a way to define the weak mixing angle. Here you will find that it's something like 120 sigma away from the theory prediction. So the theory is really bad in describing those observables because the experimentalists have done a very good job in measuring all this quantity with a tremendous precision. So all the electric data are basically known with a precision which is of the order of 1 per mil, so 0.1%. And this is here, in a sense, you are facing the fact that all the computation that I've been able to do on the blackboard are only 3-level computation. I've forgotten all the quantum correction, except these things that we computed. So the conclusion of this analysis is that basically the standard model has been tested actually at the quantum level. You cannot neglect all the quantum correction. If you neglect the quantum correction, you are very far away from the experimental data. So that's simply what we have heard many times, that yes, the standard model works very well at the quantum level. You cannot neglect the quantum correction. So how does it work exactly, right? So I'm not going to do those computations on the blackboard, and people have spent really their life in computing those quantum corrections. I mean, it's tremendous work, and it's really amazing. You can spend 30 years of your life computing loops, etc. It's not easy. All the tools are there, but physics sometimes is difficult. So how can I understand what kind of correction do I need to include to do the comparison between experiment and theory? So I say that you can compute, for instance, MW. So that was MW of the standard model at 3 levels. And then there is the correction coming from the loop. And also nobody is telling you that the standard model is really the right theory that you can use up to the Planck scale, right? So there is, in principle, new contribution coming from new physics. And let's see exactly to which level you are sensitive to this thing. So the typical correction coming from the loop, right? It's a loop of a standard model interaction, of the weak interaction. So it will typically scale, so the correction here will be MW standard model times the one loop factor, which is typically of the order of G squared divided by 16 pi squared. And clearly this is really of the order of a few per mil, right? G squared, G is of the order of 0.1, 0.2, whatever. 16 pi squared is a number a little bit bigger than 100, so it's typically a few per mil. So this is exactly what I was telling you. You cannot neglect those quantum corrections because they are of the same order as the experimental precision. So certainly, if you want to do the comparison between theory and experiment, you need to include all these quantum corrections. So what about the new physics contribution? Well, typically, if you have a new particle of a mass m, you integrate out this mass, it will give you a correction of the order of mw squared divided by m squared, if there is a 3-level contribution. So you have one W, you will mix here with, let's say, W prime. So that's a correction to the mass, a 3-level correction to the mass. And here we scale like this because you have a propagator to W prime. So it's 1 over the mass of the W prime squared. So this can also give you a correction of the order of the few per mil. This will be of the order of few per mil if m is, let's say, smaller than something like a few TeV. So let's say if 5 TeV, so MW is at 80 GeV divided by 5 TeV, this will give you a few per mil correction. Here it's, let's say, few TeV. So this means that all the electric precision data are sensitive to the presence of new physics up to few TeV. So this means that really by looking at all this kind of data, the mass of the W, the decay width of the Z into leptons, etc., you are probing really the existence of new physics up to few TeV. So here, of course, I assume that the new physics give you a 3-level contribution to this electric observable. In some model, actually, there is no 3-level contribution because of some selection rules. For instance, here, I say that there were this mixing between the W and the W prime. Okay? But if you have a symmetry, for instance, which is telling you that all the new physics, or all the particles of the new physics are even, while the standard model particle are, the new physics is odd and all the standard model particles are even, then clearly you cannot have this kind of vertex here, right? Because that will be a vertex that breaks the Z2 symmetry. Right? if you have an interaction, the interaction has to respect the Z2 symmetry, then all these interactions should be even. Here it's the product of even and odd, so this is odd. So this cannot occur. So if you have a particular Z2 symmetry that distinguishes the particle of the new physics compared to the particle of the standard model, this means that there is no tree-level contribution to the electric observer. And that's exactly what happens in supersymmetry, for instance. In supersymmetry, at least if you have R parity, this R parity is exactly doing this Z2 symmetry, distinguishing the new physics sector from the standard model sector. And in this case, you could have some loop factor suppression in front of this new physics contribution. So this is telling you in this case that you can have really new physics particle at a much lower scale without giving trouble with electric precision data. You can lower the scale without giving too large contribution to the electric observer. So usually there is a generic parameterization of this new physics contribution, at least in some generic class of new physics model, which are called oblique parameters or oblique corrections. And that's the famous ST and U parameters that sometimes maybe you have heard about them. It's just a way to parameterize in a generic way the contribution of new physics to electric observables. So I won't give you all the details, but typically, you have three of those variables. So there is MW, there is sine squared theta effective, and there is also people usually use this decay width of the Z into charge electron, plus and minus. And those new physics contribution here are basically some linear combination of the three oblique parameters ST and U. So you can compute explicitly, the factors, the linear factor in front of ST and U that relates those parameters to the physical observables. It's a little bit complicated, because here those objects are actually related to some Lagrangian, and here they are physical observables, so we need to do some computation. So there is some mixing angle occurring, etc. You don't need to know this kind of thing. So what people have done now is really analyzing all the electric data in terms of this generic parameterization. So in a sense, you can translate all the electric data into constraints into those parameters. And then any theorist, for instance, can take his favorite model, compute ST and U, and this way easily compare his model with the experimental.
Excuse me, but what is the second parameter?
T.
No.
Oh, here is the equivalent of the weak mixing angle. So yesterday we have seen that you need to perform a rotation to go from the W3 and B basis up to the Z and the photon. And this was introducing the rotation, so there is a one angle occurring there, and that's basically this angle, sine squared theta effective. Sine squared theta is not exactly equal to the weak mixing angle, because you need to take into account some loop correction, etc. But there is a one-to-one correspondence. So for instance, well, I don't know, there is an exercise that I have prepared for you, but I don't think I have time to solve this exercise in front of the blackboard. But to match with what I was saying yesterday, you can take some higher dimensional operators. That's a way also to parameterize new physics contribution, right, to the electric observables. And then you can really compute those oblique corrections in terms of the coefficients in front of this dimension 6 operator. So that's an exercise that you can do. And again, if you have some questions, you can solve it together tomorrow. So if you take, for instance, this particular dimension 6 operator, which is 1 over lambda squared, h dagger du h squared. So again, it's dimension 6, right? Because x is dimension 1. So derivative is dimension 1 also. So we have 3 power, so it's dimension 3, squared is dimension 6. And you can check explicitly that this contributes to the t oblique parameters. And this contribution is given by minus 1 over 2 square root of 2 alpha electromagnetism G Fermi. And there is another one that contributes to the S oblique parameters. This is 1 over lambda squared, H dagger, sigma A, H, W mu A, and B mu. And this contributes to the S oblique parameters. So they say this in the unitary gauge, this is simply a kinetic mixing between W3, right? In the unitary gauge, this is non-vanishing only if A is equal to 3. So this is 3 and B, so this is a mixing, if you want, between the W3 and B, or if you want a kinetic mixing between the photon and the Z gauge field. So it modifies the way the Z and the photon are propagating. And then this contributes S. What is the contribution? S. It's 4 sine theta W cos sine theta W cosine theta W divided by square root of 2 alpha electromagnetism G Fermi lambda squared. Now you can trust your experimentalist friend. We are translating all their data in terms of constraint on these parameters. So for instance, there is a famous plot that shows you this T and S. And there is those famous ellipses here. So this is 68% confidence level. This is 95% confidence level. They are telling you that the standard model is sitting somewhere here. That corresponds to S and T equal to 0 by definition. And then here, the contribution from over is of the order of 0.1. Here is the same. 0.1 minus 0.1. So from this plot, then you can derive immediately some bounds on the parameter lambda. So now, there is only one subtlety in reading this plot, is that here, I've said that the standard model is here. But what is a standard model? It's a standard model with the Higgs boson. And to characterize fully the standard model, I also need to specify the mass of the Higgs boson. So here, E is a standard model with a particular value of the mass of the Higgs boson. Typically now, people are using this beautiful mass of Higgs boson. So they do all their computation, so they compute all these loops. They compute all these loops with this particular value of the standard model, mass with the Higgs boson. And then, once you know this, then you can extract typically this new physics contribution. So this is also telling you that if you change the mass of the Higgs boson, then the standard model will move right, in this way. And typically, this is the way the standard model point moves when you increase the value of the mass of the Higgs boson. So this is for 126. And typically here you are going away from the ellipses at a mass around 200 GeV. And here if you have 500 GeV, so the mass of the Higgs is 500 GeV, you will be far away from the ellipses.
What is the value of resistance?
Sorry?
What is the value?
So it's 0.1.
Not there, but Higgs mass. 500 is too far.
Well, 1 TeV. but I mean, 500 you are already aware.
Yeah, but it is 130, for instance, away.
Well, here you're getting away from the 95% confidence level ellipses for mass at 180. Right, so here you want to use 180. So that's why, in a sense, even before the LHC observation of the mass of the Higgs, you really had some good indication where the mass should be, right? Just looking at lab data. Lab data is telling you that the mass of the Higgs couldn't be too large, in principle. Of course, it's always indirect information, so it's always possible that, you know, here you have another new physics contribution that cancels exactly the large contribution coming from the AV, from the contribution of AVX. So you have two large contributions, those two large contributions cancel, and you remain within the ellipses. But this requires some fine-tuning, right? Because you have two large numbers, and they cancel almost each other to stay within the ellipses. So this is, in a sense, not totally natural. It's possible, but it's not natural. So if you assume really that the physics has to be natural, so no big cancellation that you don't understand, then you knew that the mass of the Higgs had to be light, typically below 200 GeV. And you know, since the observation of the LHC, that the mass of the Higgs has indeed been discovered around this level. So everything is consistent. Okay.
Sorry, could you repeat? The weak mass comes from the
so from here,
comes from the loops, and
yes.
one which cancels that correction.
Well, so for instance, you know, if you have physics beyond the standard model, they could give you another contribution here that will cancel the big contribution coming from the loop of the Higgs. So that will be fine-tuning.
There is no fine-tuning within the standard model.
So within the standard model, if the Higgs is light, then this loop contribution are small enough to be within the ellipses. If the mass of the Higgs is large, then you are going away from the standard model. From the ellipses, then you need to add new physics contribution that cancels this large contribution from the Higgs. So actually you can estimate, there is some formula first derived by Peskin and Pekeuchi, for example, that give you the approximate contribution of a large Higgs boson to S and T. For some reason that I will tell you in a moment, you can totally neglect U actually. So the contribution of the Higgs to delta S and delta T is 112 pi log of the mass of the Higgs squared divided by the mass of the Z boson. The same thing for delta T is this negative contribution, minus 3 divided by 16 pi cosine theta W, and the log the mass of the Higgs squared divided by the mass of the Z. So that's exactly what I was showing you in this plot, right? When you are increasing the mass of the Higgs, you are getting a positive contribution to delta S and a negative contribution to delta T. So you're really moving along this direction. It would have been better, for instance, if delta T were positive, right? Then we could explore this ellipsis. That's not the case. Bad luck. Okay. So that was the electric precision data. That was certainly an important tool to test any model of new physics beyond the standard model. We are probing this contribution to electric themselves. So now I would like to come back to the description now of the electric symmetry breaking sector. So I would like first to have a description of this longitudinal polarization of the W and the Z. And then we will add also the famous Higgs boson and maybe something else. And maybe to derive this exercise, right, if you want to do it tonight, the last piece of information, and then you can compute these things, but the way the theorists are doing this computation is just to look at the Lagrangian and doing the momentum expansion of the Lagrangian. So you write your Lagrangian simply as some self-energy for the W plus and W minus. Self-energy that depends on the momentum of the particle, minus mu, and the same thing for W3 and B, so it's plus 1/2 of W3, pi, so here pi plus minus, here it's pi 3, p squared, and I have the same thing for the B, mu pi 0, 0 squared, and then you can also have this mixing between W3 and B, which is W3 mu, B mu, minus pi 3, 0, and then S, T, and U are simply related to the derivative, to the value of this self-energy. So the definition, I'll give you the definition, then you will know everything about electric precision delta. The definition is the following, is that S is equal to 4 sin squared theta W divided by alpha electromagnetism times G divided by G prime times the first derivative of this kinetic mixing. So pi 3, 0. So the first derivative means that you are looking at the p squared terms. Right? P squared means that you have one derivative, so it's exactly the kinetic mixing that I was referring before. Here. I say that S corresponds to the kinetic mixing, so there is two derivatives. Two derivatives mean p squared. Computed at p squared. T, so T is equal to 1 over alpha electromagnetism times T 1 mw squared times pi 3, 3 and 0 minus pi 0 plus minus and 0. If you want here, you are measuring the mass difference between W3 and the W plus and minus. So there is no derivatives, which refer to the term here without derivatives, so that corresponds to the mass term. And we're doing the expansion here of those form factors and mass term in p squared. That's what we were saying yesterday. You know, we were commenting about the custodial symmetry. So the custodial symmetry was a way to measure how the mass term for W3 is different than the mass term for W plus and W minus. So here T is really measuring, if you want, the difference between the mass of the Z and the mass of the W, up to the factor of cosine theta W that were needed to get rho equal 1. We say that rho equal 1 was the mass of the W divided by the mass of the Z divided by cosine theta W. So here T is actually measuring the difference of rho equal 1. So T will be up to the factor of alpha, because the factor of alpha that is proportional to rho minus 1. And so in a sense, T is measuring the violation of the custodial symmetry. So every time you have a theory that satisfies custodial symmetry, then you have to compute, you can compute T, and you will find that T is equal to 0. At 3 level.
Excuse me, can you repeat what is the sense of P function?
It's just some form factor, right? I mean, you're just writing your Lagrangian, so for instance, you know that in the standard model, you know that this is just the mass plus the kinetic term, so it's pi in the standard model will correspond pi will correspond to the mass plus p squared minus p squared, whatever is always a sign, because there is a kinetic term, there is a derivative. But in a general theory, you can get some additional terms because the W and the Z mix with all the states, they mix with the W prime, etc. And this will give you some correction to this standard model prediction. And that's exactly what S and T are measuring. They are measuring the deviation compared to the standard model.
But you have 4 different P, I mean P plus minus, P.
Yes, because that's the Lagrangian you can write, which is invariant under U1 of electromagnetism. So this, you have to write something which is electrically neutral, right? So that's why I have W plus W minus. Here the W free and B don't carry any electric charge, so you can mix them. So that's the most general Lagrangian that you can write for the standard model degrees of freedom, which is invariant under U1 of electromagnetism. So that's the Lagrangian after electric symmetry breaking. Yeah, yeah, you can take this as a definition. Or the other way to define that is through the derivation that I've sketched here, that you can really compute those observable in terms of those observable, and then there is a definition in terms of linear combination of ST and U. From the theoretical perspective, it's easier simply to define S and T this way, because they are directly related to Lagrangian. So you can compute your Lagrangian, by diagonalizing and integrating out any degrees of freedom. You will obtain this Lagrangian, and then you can read off directly S and T. So for instance, here it's a very trivial exercise. You take those higher dimensional operators, write them in the unitary gauge. You will easily read those pi factor, and then you can compute S and T immediately. There is no computation. You don't have to compute any Feynman diagrams or anything. It's simply linear algebra that you can do with Mathematica. So I really encourage you tonight to do this computation of S and T. It will always be useful for you in your life. Believe me. Okay, good. So far so good for electric precision data. So let us come back now to the description of my longitudinal polarization of the W and the Z. So in a sense, I'm totally agnostic. I don't know what the standard model is. I just know from experimentalists that there is a mass for the W and the Z, and associated to those mass, I have some longitudinal polarization, and I want to have a Lagrangian to describe those objects. The Lagrangian to be able to do some computation. Yes.
It's just suspicious a little bit. Pi is in square or without square?
Here there is no square, right?
Without square.
So it's a function of p squared.
Not square.
It's a function of p squared because it has to be Lorentz invariant, right? So p mu should always occur as a Lorentz invariant contraction.
Does it have the sense of some energy, no?
Yes, true. So here, if you want, you're right that if the W were on shell, then p squared would be simply the mass. But if you want a Lagrangian to describe so also some off shell W.
In the upper formula, you should write square. I mean, pi is equal m in the power of 2 plus 3 in the power of 2.
That's a function of pi. Okay.
And pi, not squared pi.
No.
Okay.
No.
Thank you very much.
Sorry. Can you repeat what is the task?
What is what?
The task works.
Oh, for the exercise, so just take this higher dimensional operator. So you take the Lagrangian of the standard model and you add this dimension 6 operator. So in principle, they are not there in the standard model. When in the standard model, you have a Lagrangian that stops at dimension 4. Because there has to be a renormalizable Lagrangian. It was a big deal in the 70s, right? Everybody wanted to have a renormalizable theory. But now we know that effective field theory with higher dimensional operators are perfectly fine. They are just valid up to an energy scale, which is associated to the scale that suppresses those higher dimensional operators. So just, they are not theory that you can extend up to arbitrarily high energy, but you can do a lot of computation with them. For instance, all the pion physics in QCD, you can really describe them in terms of an effective field theory. And you can do a lot of computation without knowing that the pion are made of quark. The quark will appear at higher energy, above the mass of the pion, but you can describe perfectly the physics of the pion with an effective theory. So here is exactly the same thing. We have discovered the Higgs, we have discovered this longitudinal polarization of the W and the Z, and we want to have an effective theory to describe these degrees of freedom. So that's what I'm doing here, in a sense, right? I'm trying to write a more general Lagrangian that respects certain symmetry to describe those degrees of freedom. And then, you know, you will compare to the data, so the data will basically give you the value of the coefficient in front of those operators, and then later on, maybe in 10 years, you will be identified what the theory is that gives rise to these higher dimensional operators. But that's the next step. The next step will be to look at the UV completion. So what are the new degrees of freedom that give rise to this higher dimensional operator when they are integrated out? For the moment, we have a very pragmatic approach. We have some degrees of freedom, and you want simply to describe, you want to have a Lagrangian to describe the physics of those degrees of freedom at the energy that you can probe directly at the energy. So the exercise is very simple. You take these operators, and the exercise is to compute S and T. And then compare with this kind of plot, for instance, to put some bound on the scale of lambda. Okay. Any further question?
What about the third parameter?
Yes, okay, good question. So here, I told you that you have two dimension 6 operator that give rise to S and T. And actually you can check that there is no dimension 6 operator that will give rise to U. So I haven't defined U. I can give you the definition of U in terms of the time. U, where is this? Yeah, you're right that here there is 3 parameters, but nobody usually is talking about the third parameter because in most of the theory, U is equal to 0. And the reason is that U is defined as -4 sine squared theta W divided by alpha electromagnetic. The derivative of this pi plus minus evaluated at 0 minus pi 3. So if you want, T was the difference in the mass, and U is the difference in the kinetic term between the W3 and W plus and minus. So now you can check that there is no dimension 6 operator that gives rise to U. So if you write all the possible dimension 6 operator, you compute, you will always find that U is equal to 0. So U can only occur via dimension 8 operators. So this means that it will be further suppressed, and in practical terms, you can always neglect the contribution of U. So when you are looking at the data, I was here plotting this experimental constraint S and T, and here it's done assuming that U is equal to 0. In practical terms, for any physical model that are interesting for you, U will be always equal to 0, or much smaller than S and T. You can neglect it. So that's exactly what I wanted to cover yesterday, so we are a little bit late. Okay. So let us come back now to this longitudinal polarization of the W and the Z. So yesterday we have seen really that there is a connection between those longitudinal polarization and the Goldstone boson associated to the breaking of the custodial symmetry, or if you want, the breaking of SO4 down to SO3. That's what I reminded you at the beginning of the lecture today. I reminded you that you could see the longitudinal polarization of the W and the Z really as a Goldstone boson associated to the breaking of SO4, or if you want SU2 left plus SU2 right, broken down to the SU2 diagonal, which is SO3. So we have seen that this gives you exactly 3 Goldstones. And what the Goldstone equivalent theorem is telling you is that at high energy, for energy which are in principle much larger than the mass of the W and the Z, you can really describe the physics of those objects in terms of those Goldstone bosons. And that's a very useful thing, because the longitudinal polarization, 5 minutes. The longitudinal polarization of a spin 1 is a complicated object. I mean, you have a lot of Lorentz indices, etc. Here, it's simply a spin 0 particle. So it's an object which is simple. There is no weird Lorentz indices, nothing. There is no gauge symmetry associated to it. So there is no redundancies of the degrees of freedom. You don't have to worry about fixing the gauge, etc. So the computation will be much simpler using this parameterization. And this will certainly give you a good description of the physics of those objects at the LHE energy. At the energy which are higher than the mass of the W and the Z. So you can try really to build the chiral Lagrangian for those objects. And now this is very similar, if you want, to what you are used to in QCD for the pion, for the physics of the pion. In the sense, those Goldstone bosons are nothing else than the pion. It can be described as pion of QCD. Pi plus minus, pi 0. And actually, it's exactly the same symmetry, right? You know that in QCD, you also have SU2 left plus SU2 right broken to SU2 diagonal associated to the mass of the up and down type quark. If you neglect the mass of the quark, you exactly get this symmetry, and that's the reason why the pion in QCD are much lighter than the typical resonances of the QCD. Right? So they are of the order of 100 of MeV, while all the other resonances are close to 1 GeV. The mass of the proton is 1 GeV. The mass of the pion is much lighter, is much smaller than the mass of the proton, simply because the pion are really some Goldstone boson. So if you neglect the mass of the quark, the Goldstone will be exactly massless. It will be exact Goldstone boson. They acquire mass because in real life the quark are not massless particles, so the mass of the up quark, the mass of the down, in a sense, are an explicit breaking of the global symmetry under which the Goldstone appears as Goldstone boson. So it's a perturbation around the exact symmetry. And that gives rise to the mass of the pion. So here, the way to deal with this object, this longitudinal polarization of the W and the Z, is exactly like in QCD. So to introduce an exponential of the pion. So you introduce this matrix sigma, which is nothing else than exponential of I A, sigma A, divided by E. So in QCD, here you put F pi, the decay constant of the pion, and here, for this object here, you will simply introduce a scale which is associated to electric symmetry breaking, and it will be V, which we will identify later on as 246 P, related to the Fermi constant. And here, this matrix sigma, this exponential of the pion, really transform in a simple way. If you apply a SU2 transformation, you will simply transform it. So you have SU2, so this is a big matrix, right? A 3 by 3 matrix. You can apply a SU2 transformation on the left, so the U1 hypercharge transformation on the right, and eventually you can promote that to a global symmetry, which is SU2 right. So that's exactly the transformation property of the sequence. Now you have to realize that SU2 plus 1, if you look at the transformation of the pion, they will act non-linearly. They will transform non-linearly over this gauge symmetry. So that's a non-linear realization of the gauge symmetry. You know, sometimes you hear that the mass of the W and the Z are breaking the gauge symmetry. This is not true. The gauge symmetry is never broken. If you have a mass, the symmetry is non-linearly realized. The sense of the symmetry transformation are non-linear on the physical degrees of freedom on the pion. And then the way to write simply the mass of the W, and we stop here, the mass of the W and the Z, that's 1/2 the mass of the Z squared. We'll see that is nothing else than V squared divided by 4, the trace mu sigma Higgs mu sigma, where d mu sigma is a covariant derivative, associated to sigma, so this is d mu sigma minus I d divided by 2 W mu A sigma A sigma plus I divided by 2 G prime mu sigma sigma. So what do I mean by this? So what do I mean by this is that this identity here, that's the second exercise that you can do tonight, we'll come back to it tomorrow if you have problems, that here, this identity is really following from the unitary gauge. If you go in a particular gauge where sigma is just equal to the identity, you have sigma here, definitely you can perform a gauge transformation, so you choose appropriately G left and G right in such a way to get rid of sigma. So you go to the unitary gauge where sigma is equal to identity, then the derivative is 0, and here you simply get W and B. So this kinetic term is nothing else than the mass to the W and the Z. So that's the correct way to really describe the mass term of this longitudinal polarization at high energy. Simply as the kinetic term to the Boson boson. So the advantage of this description is, of course, that here you also contain some nonlinear interaction. So you can expand this exponential. There will be some term that correspond to the kinetic term. So by doing the expansion of this exponential, you will find that it contains d mu pi squared. So this means that pion are canonically normalized, maybe 1/2. But you will have also some term that we will compute tomorrow that goes like pi d mu pi squared. So an interaction between 4 pions and 2 derivatives.
And the equation of V power 2 divided by 4 and between the bracket, it's what? It's a trace?
So here it's a trace, yes. So here you have some matrices, right? So here, by doing this expansion, you will have some term, some interaction term between 4 pions, and those interactions will be growing with the energy because they have some derivatives. So this means that I will have an interaction pi pi goes to pi pi with a cross section which is growing with the energy. That is, the amplitude is growing like E squared. So we compute that is E squared divided by P squared. And of course, you cannot have a scattering amplitude which is growing with the energy, because at some point, the cross section will be becoming too large, and you lose unitarity or perturbative unitarity. So the theory won't. This description will break at some point. It will break at an energy which is related to the scale here, and there will be a cutoff, and the cutoff we will identify as 4 pi times p. So it's a description of those longitudinal polarization which is valid at an energy above the mass of the W and the Z, up to an energy which is 4 pi times p. So it's a small window where you can really look at the physics of this object and try to infer what real physics would. And we will see that in order to cure this problem, basically you need to add a new degree of freedom, which is the Higgs boson. So that was the Higgs boson was really needed. There is no consistent description of the longitudinal polarization of the W and the Z if you don't add any new degrees of freedom. We needed something that looks like Higgs boson to make the theory consistent up to an energy scale which is much larger than this one. Okay, I think the time is over. Continue tomorrow. Thank you.
We have a lot of very interesting material, so you should have questions.
No. I don't understand your last assertions. Can you repeat it?
So we'll
We'll
come back tomorrow.
I don't understand your last statement about the consistency.
We'll come back to that tomorrow, but it was just a preview. Here I say that the mass of the W and the Z, you can rewrite it here as a kinetic term for the Grojean boson. But then, looking at this kinetic term, you will identify some interaction among 4 Grojean bosons that grow with the energy. So you are computing a physical process which is W goes to W, if you want pi pi goes to pi pi, and this grows with the energy. So this means that this
amplitude contains derivative,
right,
as Christophe just told. He rewrite mass through derivative, so amplitude proportional to momentum. That's why it grows with momentum.
Right. Yeah, here we have some momentum dependence, so the momentum is the energy, right? So the process grows with the energy, and at some point, the cross-section will be too big to make sense. It won't be consistent with quantum mechanics. Cross-section is a probability, and then if the cross-section is growing, the probability is growing, and then it will become bigger than 1. It's not possible.
Okay. More questions, please.
Can you repeat how?
Because everybody should listen to your question and think about.
Can you repeat how did you get that equation lambda is equal for P?
We'll come back to that tomorrow. Here it was just a preview, so telling you that there is a scale associated. The cutoff scale at which your theory doesn't make sense anymore.
And the V at that V?
Yes, 246 GeV, the weak scale.
Okay, more questions, please.
I mean, in a sense, it's not a surprise. I mean, you know that in QCD, there is a cutoff associated to f pi. Lambda QCD is 4 pi times f pi. And this is exactly the same thing as in QCD. So what happened in QCD is that, of course, you have the pion, so pi scattering will grow with the energy until you are reaching the new resonances of QCD, which is typically the rho meson. And if you put the numbers, it exactly works. I mean, the rho meson is about 4 pi higher than the mass of f pi, in such a way that the exchange of the rho meson will unitarize your pi scattering. So there is a total analogy with QCD.
More questions, please. Wait.
The only thing is that in QCD, the unitarization proceeds via strong interaction. I mean, you have QCD, the QCD interaction are becoming strong, they are producing resonances. Here, we don't know yet if the physics behind the unitarization of WW scattering is weak interaction or strong interaction. So the hope is that the Higgs somehow is a new mechanism with which is weakly coupled, so the physics remain perturbative, and there is no resonances, no bond state appearing. So that will be the main difference between.
Last question, please, because
Sorry, maybe I skip it, but what does it mean formulas delta S and delta T?
Well, it's just a contribution, S and T coming from a heavy Higgs boson.
And in standard model, S and T parameters are not zero.
They are zero for a reference value of the Higgs mass, right? Because to define S and T, I needed to compute all this loop of the standard model. But those loops are defined for a particular value of the Higgs boson mass. If you change the value of the Higgs boson mass, then you will get an additional contribution of S and T.
Yes, keep it. Okay, thank you.
that's all. Maybe I have one question to you. When Christophe talked about this parameterization of new physics through STU, the question is why there are only 3 parameters, STU? Not 4 parameters, not 2 parameters, only 3. You can think about this.